Right, internal resistance and EMF for a cell. Okay, it's not going to get more straightforward than this, I think, in terms of internal resistance. Right, state what the EMF of a battery is. Okay, this is marked. This has got to be 2 marks in the bag for every single one of you, surely. Okay, right. What's the textbook definition of EMF? Okay, so EMF is the work done per unit of charge. Okay, so work done per unit of charge, or the energy per unit of charge given to the electrons in a circuit, or the work done per unit of charge converting from chemical into electrical. Okay, please, you have to learn these definitions. Please don't try and trip yourself up by trying to say something slightly different, because in some cases you'll miss out on the marks. Okay, add to the diagram. So how do we connect an ammeter? Yes, with wires, but we've also connected in series. Voltmeter in parallel. Easy peasy. Okay, right. What could be the problem if we if we take the resistance of a resistor to 0? If we take that to 0, this just becomes a wire. Now, if we have a small internal resistance here, that's going to produce a very large current in the circuit, because we have very small resistance in the total circuit. So it's going to overheat. It's going to overheat and get very hot. Okay, right, there's the graph. Yeah, we've got, so the voltage is the voltage across, remember, the load here. Yeah, so that's in this core practical, that's the thing you measure, isn't it? The voltage across the external load, because you can't measure the voltage across the internal resistance. Right, so there's our results. Okay, yeah, you should all know this, but we need to draw a nice straight line of best fit through. Now the points are quite nice. Let's try that again. The points are quite nice. Doing this on a screen is tricky. The points are quite nice. Okay, so in the internal resistance is the gradient, and the EMF is the intercept. Okay, so we're looking like an EMF of 6 volts. Now, internal, just be careful here. It might look like it's straightforward. You know, they're very, very nice points. They're all in a straight line. Okay, and that's not a gift to make it easier to you. That's to see how careful and accurately you can draw a line of best fit. So yeah, just being a bit careless here, thinking, oh, it's an easy one. You could well have missed out on the range of values accepted for R. Okay, but yeah, as we know, it's the gradient. So it's okay, Y change over X change. So we're looking at, going by my line of best fit. Okay, let's say 5.8 minus 1 all over 1.2. What does that give me? It's different to what I did before. Minus 1 equals divided by 1.2. So, but yeah, 4 ohms. 4 ohms. Right. What did? See on the mark scheme there, 4.05 to 4.25. That's what's available to you. But yeah, I drew it in cami, so I'm allowed. Right. Power transferred from the battery to the load resistance. Right. When R equals R. Now, it's very, very useful sometimes, or lots of times, to think about a cell with its internal resistance and an external load as a potential divider. Always really keep that at the forefront whenever you look at any internal resistance question. Okay, it's literally a potential divider. situation because we've got two different resistors in series. Okay, now we got a value of, okay, so the internal resistance was about 4 ohms. So if R equals R, then that's going to be 4 ohms. Yeah. If that's going to be 6 volts, then the voltage across this guy is going to be 3 volts. Okay. It wants the power dissipated in R. Remember, this is big R. Okay. Right. Power equation. There's 3. The one we want here, well, we've got V, we've got R. That looks like it could do a job. Okay, so 3 squared is 9, R is 4. 9 divided by 4 is 2.25 watts. Okay, yeah, that caught out a lot of people. Loads of you went with the V as this value here. Okay, but if you'd have drawn that as a potential divider, you would have seen immediately that that cannot be the case. Okay, that is, I believe, yeah, that's question 14.